Okay, here we are. We have a series of problems involving three strings. I'm going to go pretty quickly through these because we remember them from last time, from when we covered them. First, we have a 45 kilogram block being supported by three ropes depicted below. The ropes and the block are at rest. Total force is 0. Left's balancing right. Up is balancing down. The forces balance. Whenever you see at rest, if the object remains at rest, make sure you underline it and show, and just a good practice, to remind yourself, you don't have to, but just to remind yourself, consider writing out what I just put. The tension in rope 2 is 260. That means the two ends are pulled in with 260. Find the tension in rope 1. The two ends of rope 1 are being pulled back to the middle. The value of the tension is T1. Now, assume the ropes are ideal and have no mass. That means don't draw force arrows for the rope's weight. They don't have any weight, no gravity, no mass. Good. Now, this rope 3 has been stretched, so its ends are being pulled toward the middle. And of course, the force of gravity pulls down on our block. Mass is 45 times g. If we use 10, then mg is 450 newtons. Because that block doesn't move, up T3 balances down 450. T1, we are almost. T1 has an x component and a y component. The x component I'll just call Tx. The y component I'll call Ty. This intersection is in equilibrium. That means at the intersection, the forces pulling left on the intersection, forces pulling left, which are Tx, balance or equal the forces pulling to the right, which is 260. So we just found that the x component of the tension, T1, the x component of T1 is 260. And at the same intersection, which is at equilibrium, the down force, which is 450, balances the up force, Ty. So T1 is simply found from the Pythagorean theorem. It's x component squared plus its y component squared, all square rooted. So we solve from there. Plug in the values, and T1 comes to, let's see, square root 260 squared plus 450 squared. Boop, beep, boop, 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 beep, boop. 5. Let's just call it 520. It's 519.7. And when we round to the nearest whole number, we get just 520. Next problem. A 14 kilogram block is being supported by three ropes depicted below. The ropes in the block are in equilibrium. Find the tension in each rope. The ropes are ideal and massless. Alright, so first start at the block. Gravity pulls it down with mg. M is 14, g is 10. 14 times 10 is 140 newtons because it's force. T3 has been stretched. So the ends of the rope 3 are pulling back toward the middle, and the value of tension is going to be 140 because the block is in equilibrium. So up balances or equals down. T3 equals the 140 pulling down. Now, we also have tension in rope 1, so that's being pulled up, T1. This is T2. Look, we just found, by the way. Let's go ahead and list that answer. Whoops, 140. Where did I get 450? Okay. So there's one of the tensions. Two more to go. T2 and T1. We can't find T2 yet. We're going to be balancing forces at the intersection I just drew. But the left force is Tx, or T1x, whatever you want to call it. And the up force at the intersection is Ty. So we know Ty balances T3, the down force at the intersection. And we know T2 balances Tx, the x component of T1. We don't know this or that, so we can't start with that equation. We have to start with this one. So Ty is unknown, but T3 we have. It's 140. Ty is replaceable with hypotenuse, T1, times the sine of theta. Solve for T1, and we get 48, 188 newtons. Now, over here, we can find T2. So look, T1 and T3 are both known. T2 is the last one. We can find T2 because T2 equals Tx, and Tx is replaceable with T1 cosine the 48. T1 we found to be 188. T2 comes out to be 126. Alright, next one. A block's being supported by 3 ropes depicted below. The ropes and the block are at rest, and they remain that way. We can clearly see they're going to remain that way. Nothing is changing their motion. So the total force is 0, forces balance. The tension in rope 1 is 49 newtons. Rope 1's ends have been stretched, so tension pulls them back. Tension pulls those ends back toward the middle with 49. Rope 1 is angled at 39 degrees. That'll be important. Up from horizontal, like I've shown. Find the tension in rope 2. And we also have to find the mass of the block. So rope 2, tension pulls it to the left. There's tension in rope 3 because it's been stretched. And of course, pulling down on the block is mg. Step 1, you see, I just did it. Step 1 is draw all your forces on all of the objects. Okay. Now, the next thing you're going to want to do is draw the components of 2D forces. The green arrow pointing right is equal to 49 cosine 39 degrees, hypotenuse cosine theta. And it balances T2, because the rightward pulling force on the point balances the leftward pulling force. Equilibrium, balancing. In addition, we know that the upward green arrow, which is 49 sine theta, the upward force acting at this point balances the downward force at the point, T3. So just like that, we can find T2 and T3. T2 comes out to be 49 cos 39. This is 38.1 newtons, and T3 is the same thing but with sine, so it's going to be 30.8. Alright then, we look at our block right here. The up forces, which are T3, balance the down forces, mg. T3 is 30.8. M is our unknown. G, we are using 10. We divide both sides by 10, and you get mass is 3.08 kilograms. Next, a system of ropes is in equilibrium. It's shown below. Find the tension in rope 1, in rope 2, rope 3, and the mass of the middle block. So, in other words, find the tension in each rope. Assume they are ideal and massless. use G equals 10. Step 1, draw all the forces. Gravity pulls this thing down with 120 newtons. M is 12 times G 10 gives us G, which is 10, gives us 120. Rope 3 has been pulled up, so they're stretched down, so it's being pulled back up toward the middle. It resists the downward stretching by pulling back up. And then at this point, T3 is pulling along the angle toward the middle. T2 has also been stretched. Rope 2, rather, has been stretched. So there's tension. The rope's ends are being pulled back to the middle. T1 has been stretched, so its ends are being pulled back to the middle. And this has been stretched, that rope, which is not numbered, and so has this one. Pulling down on the block is mg. Pulling down here is 180 newtons. M 18 times G 10. G, which is 10, gives us 180. Alright then, we balance the forces on the 12 kilogram block. We see T3 is 120. That means this T3 is 120. At this point, the right forces, which is 120 cosine 37, balance the left forces, which is T2. So we'll be able to find T2. Moreover, the up forces, which is the y part of T3, the up forces, which is 120 sine 37, right? That's the magnitude of my up arrow, balances the down arrow. But this down arrow is equal to that down arrow. Sorry, this down arrow is equal to this up arrow, and the up arrow balances mg. That means this also is mg. And what is it? The 120 sine 37. What does it balance? It's balancing mg. So we'll be able to find m from that. So let's go ahead and calculate. Coming back down here, we get T2 is equal to 95.8. When we solve for mass by dividing both sides by g, we get 7.2 kilograms. Okay. Now look at this block on the far left. It is in equilibrium, so its down force balances the up force, and that upward tension has to be 180. If the upward tension is 180, then the downward tension at the other end is also 180. The tension in the two ends of the ropes equal. Okay. So T1 is the final thing to calculate. T1 has an x component, which I'll call Tx, and a y component, which I'll call Ty. Looking at this point now, Tx, the only leftward force, balances the only rightward force, T2. So Tx is equal to 95.8. And then we can also see that Ty, the y part of T1, balances the only downward force at the point, which is 180. So we've balanced the left and right at the point. We've balanced up and down at the point. So T1 we can find from the Pythagorean theorem. Right? It's going to be Tx squared plus Ty squared. And we replace Tx with the value that we have below that we just wrote down. Tx is, where is it? 95.8. Ty is 180. When we calculate T1, we get 204.